This program is brought to you by Stanford University. Please visit us at stanford.edu.
We won't get to Bell's theorem, but that's okay. We can do that next week. I hope we get to entanglement. All right, but we were in the midst of still... entanglement has to do with what happens. The simplest case of it is when you have two electrons with their spins. Forget the fact that electrons can move around, just worry about their spins. Entanglement is what happens when you have more than one system and the kind of interesting quantum states that can be made for systems which have parts to them, more than one part. We're still struggling through trying to understand the simplest quantum system, the one bit or the one quantum bit system, the spin, the two-state system. And I wanted to finish that up because it will come in a very central way, all of the things we are talking about the simple spin system. The last time we talked about what happens if you're interested in the component of spin along some axis which is neither 3, 2, or 1, but along some arbitrary axis. And the arbitrary axis can be represented by a unit vector, a unit pointer that has components n1, n2, n3. Incidentally, okay, so here's my coordinates in space. I guess I've called this one 1, this one 2, this one 3. And I may lapse every now and then into calling 1 x, 2 y, and 3 z. So keep in mind, I've tried not to. I've tried to keep a consistent notation in my notes. But I do have that habit of sometimes going back and forth from 1, 2, and 3 to x, y, and z. And then, if you have an ordinary vector in space, not this unit vector in particular, but some other vector, yes? Is that right-handed or not? I intended it to be right-handed, but I can x. I think so, but my shoulder was broken, and I don't think I can do it. It doesn't matter. 1, 2, and I mean, it does matter, but is it right-handed or isn't it? No? It's left-handed. Okay, so then we have to have y going into the board. All right, then we have to have y going into the board, but.
Although you could have just relabeled y and z could have come out.
Yeah. Indeed. But my broken shoulder is limiting my my orientation. All right. Now, if you have some physical vector, thing that you can measure, in particular, a thing that we've represented as having components sigma x, or sigma 1, sigma 2, and sigma 3, this is supposed to be some physically measurable little magnetic moment or spin vector. It has components along the 1, 2, and 3 axes. We can call them sigma 1, sigma 2, and sigma 3, and we have called them sigma 1, sigma 2, and sigma 3. Those are observable quantities, and we represent them by matrices. But for the moment, forget that they're matrices. If we're interested in the component of sigma along the arbitrary axis n, then what we're interested in is the dot product of sigma with n. And to indicate a unit vector, it's conventional to put a little hat on top of it. If it's a unit vector, then let's just write down a couple of equations. n1 squared plus n2 squared plus n3 squared is equal to 1. Okay, that's the definition of a unit vector. And sigma dot n, this is the ordinary space dot product, not the inner product of two abstract vectors representing states, but just the ordinary dot product in space of a vector that we can measure, whose components are measurable quantities, and the unit vector n, then this is by definition n1 sigma 1 plus n2 sigma 2 plus n3 sigma 3. But now each of the sigmas is itself a matrix. The n's are just numbers. The direction cosines of some direction is what they are. The direction cosines of some direction. And, but the sigmas are matrices. And so this whole thing is itself, matrices or operators, if I want to be really technically correct, linear operators. But let's just think of them as matrices. And then remembering let's write down what the matrix is. Okay, so sigma 3, remember what sigma 3 is? It's the matrix with a 1 and a minus 1. So that means we would multiply it by n3 and put n3 here and minus n3 here. Sigma 1 has a 1 over here and a 1 over here. So we would put an n1 over here and an n1 over here. And then sigma 2 has a minus I and a plus I. So we would write plus I, and let me make this bigger. N1 plus I N2. And then down here it would be N1, no, sorry, minus I N2. And here it would be N1 minus plus I N2. And then minus n3 over here. Notice that it's Hermitian. The diagonal elements are real. The off-diagonal elements are complex conjugates of each other. That makes it Hermitian. And I'm going to just make a little notation. I may or may not use it very much, but it's a standard notation to write that n1 minus I n2 is equal to n minus, and n1 plus I n2 is equal to n plus. Just definition. Okay. Let me write another interesting simple equation. If you multiply n plus, then we can just write that this is equal to, and simplify the expression, n3, n minus, n plus, minus n3. That's the matrix sigma dot n, and it's supposed to be an observable, something we can measure. We measure it by putting the electron or suddenly turning on a large magnetic field oriented along the n-axis, and then checking whether it does or doesn't emit a photon. If it doesn't emit a photon, then it has positive component of sigma dot n. Okay, now one thing that we checked last time, I believe we checked last time, was that for any n, sigma dot n squared is equal to 1. You can check that either by multiplying this matrix by itself and then using the fact that n1 squared plus n2 squared plus n squared 3 squared equals 1. Or you can check it from the fact that each one of the, well, you can check it from properties of the sigma matrices, from the sigma matrices themselves. I think did I work that out last time? Yeah, and it follows from the fact that any one of the sigmas times any one of the other sigmas is equal to minus sigma j sigma I, for I not equal to j. So sigma 1, sigma 2 is minus sigma 2, sigma 1, and you can check that easily that the square is equal to 1. Now, I'm not going to prove this right now. It's a I can't prove every single little detail of everything we do because it would take forever. So here and there, if I say something that you don't know, usually it usually means it's something that takes about a half a line to prove, and you can prove it. Think of it as a homework assignment. Okay, so if sigma dot n squared is equal to 1, well, if a number squared is equal to 1, that means that the number is either plus or minus 1, right? If a matrix squared is equal to 1, it means its eigenvalues are all plus or minus 1. So sigma dot n, in fact, has for any n, has two eigenvalues, 1 plus 1 and 1 equal to minus 1, as you might expect, corresponding to the two possibilities that when you measure the spin along that axis, you either get plus or minus. So for sigma dot n squared is equal to 1, that's one fact. Another little algebraic fact, which is kind of neat, if you multiply these, I don't know if it's neat, it's true, that's all. If it's n plus times n minus, that's equal to n1 squared plus n2 squared. Oh, notice that n plus and n minus are complex conjugates of each other. So n plus n minus, n plus n minus is equal to n1 squared plus n2 squared. Now this is a true statement. All right, let me add to this plus n3 squared and then subtract n3 squared. I haven't changed it. And now I see that n plus n minus is equal to 1 minus n3 squared. 1 minus, I don't want to square the whole thing, I only want to square the n3. That's a useful little algebraic fact that if you do the homework, which I'm going to assign for you, you will use over and over again. But it's not anything deep, it's just a little algebraic fact. Okay, here is the question. Ultimately, the question I want to ask is the following. Supposing I orient a spin, I prepare a spin by putting it in a large magnetic field, waiting for it to decay or not decay, and I force it into along a particular axis. Supposing I force it to be along the n-axis. Then I measure the component of the spin along a different axis. Let's call it the m-axis. Here's the m-axis over here. What's the probability that if I make the spin with its spin along the n-axis and then measure it along the m-axis, I will find that it's plus along the m-axis, and of course the opposite probability that it's minus along the m-axis. This is the central kind of question that quantum mechanics deals with. For the simple spin, electron spin, this is about the only interesting question that you can ask. Question? Okay. You could also, of course, ask, supposing you orient it along the m-axis and measure it on the n-axis. By symmetry, it's pretty clear that they should be equal to each other. And furthermore, you might even expect that the rotational symmetry of the world should mean that the answer only depends on the angle between n and m. That would be a nice thing to discover, and in fact it's true. The answer only depends on the angle between them. That's going to be part of your homework assignment. But how do you do it? Okay, so we have to go back then to the basic probability postulate about quantum mechanics, that what we first do is calculate the eigenvectors of sigma dot n and the eigenvectors of sigma dot m. Now, we first find the eigenvector of sigma dot n that corresponds to spin pointing definitely along this axis. And then we take the inner product with the eigenvector of sigma dot m corresponding to spin pointing along this direction. So we could write this out. Let's make a notation. Okay. Question? No. Yes?
Yeah, you just told us that sigma 1, 2, and 3 are spin operators. Does quantum mechanics tell us that, or did some experimentals tell us that?
Well, it's no single experiment. It's the whole accumulated, I mean, it's, how to say this? There was a whole lot of data about this. You could do this experiment over and over and over again, and eventually you would discover that the probabilities, that there are probabilities, that's an experimental fact, that the probabilities are given by the formulas we're going to write down. That was something that was deduced by guessing. It was guessing. It was brilliant guessing. And who guessed it? It wasn't any single person. It was a build-up from the work, first of all, starting with Einstein, who was the first to realize that quantum theory involved probabilities, and then Born, and then Heisenberg, and then Dirac. So there was a series of steps in which all of this was eventually discovered. Now, nobody has ever understood what the hell Heisenberg was thinking when he invented matrix mechanics. Nobody understands what mystical experience or what he was smoking or what, but he did. And I think you simply have to take quantum mechanics as defined by matrix mechanics as an experimental fact. It can't be derived from anything. It's not something you can derive from anything else. It's a set of empirical facts which are summarized by this calculus of probabilities. Okay, so let's first invent a notation. First of all, I'm going to invent a notation for the eigenvector of sigma dot n equals +1. And I'll just call it the vector, the eigenvector of sigma dot n with eigenvalue +1. What does it satisfy? It satisfies that sigma dot n equals 1 if you apply sigma dot n to it, you just get the same vector back. This whole elaborate thing here is just a statement that I'm talking about the eigenvector of sigma dot n with eigenvalue +1. If I apply sigma dot n to such an eigenvector, I just get 1 times the same vector. Okay, that's the eigenvector corresponding to a state. We can call it an eigenstate. The word eigenstate is also used all the time. This is the eigenstate of sigma dot n such that sigma dot n, if you measure it, is definitely equal to +1. We can do the same for sigma dot m. Sigma dot m on the state sigma dot m equals +1 also equals sigma dot m. This equal here is not an equals. It's just part of the notation labeling the vector. Okay. I could have used a simpler notation. All right, so what do we have to do? The first step is to construct these vectors, to find out what the eigenvectors of sigma dot n are and sigma dot m. And then when you've done that, you construct what is called the probability amplitude. First step is the probability amplitude. That's the inner product between the prepared state and the final outcome whose probability you're interested in, sigma dot m equals 1. All right, this is the probability amplitude that if you create an electron with its spin along the n-axis, and then you measure it along the m-axis, that you get 1, that you get +1. This is not the probability. This is the probability amplitude. To get the probability, this is a complex number in general. You square it. You multiply it by its complex conjugate, which is labeled by 2 bars and a squared. The absolute value of it squared. That's the probability. We can call that the probability that, I don't want to write all this out. It's the probability that if sigma dot n is equal to 1, and then you measure sigma dot m, you'll get 1, as opposed to -1. Okay. That's the kind of thing that quantum mechanics calculates. That's exactly what quantum mechanics does in every single case. It asks a question, what is the probability that you'll get a certain outcome about a particular variable, given that you've prepared the state in some way, perhaps involving some other variable?
One notation in probability is that you use the given as a subscript.
Yeah.
And then what you test for is the parentheses.
Okay, so we could then write the probability that if sigma dot n equals 1, then sigma dot m equals 1. And the probability in general will be less than 1. Well, let's think of some cases. If n and m are equal, then obviously the probability is 1. If n and m are opposite directions, then that's just a question, what's the probability if the spin is up, then it's down? Well, that must be 0, so we should find that. What about at 90 degrees? A half. Anywhere is in the plane. If m is in the plane perpendicular to n, we would expect to get the probability being a half. And that's true. But how do we justify it? How do we actually calculate it? So I'm going to take you through the calculation of the eigenvectors. But then you are going to go home and take their inner product. I'll take their inner product, but then you'll square it and boil it and cook it and stamp on it and cry. And it's an ugly little calculation. It's not a pleasant one. No, it's not very hard. It took me about 15 minutes. But I used a lot of tricks, which means it took me a lot longer than it will take you without any tricks. Okay, so let's find the eigenvector. Now, first of all, when you start looking for eigenvectors, we're going to try to solve the problem. Sigma dot n, where is it? It's n3 minus n3 and minus n plus. That's sigma dot n. And we're going to look for a vector, alpha beta, such that we get alpha beta back. Now, in the first round, I'm not going to worry about normalizing the vector. Later on, we can normalize the vector. Normalizing it means multiplying it by some constant so that the sums of the squares add up to 1. But for the moment, let's not worry about that. And if I don't normalize the vector, also another thing, I don't think I've ever mentioned it. All of the physical quantities in quantum mechanics are insensitive to multiplying the vectors, any one of the vectors, by a phase. A phase means a complex number of magnitude 1. And the reason is because all of the physical quantities, you always complex conjugate them and square it. And the complex conjugate and a number whose magnitude is 1, a number like e to the I theta, it will not enter into any probability that you ever calculate. So if you take a vector and you multiply it by the number e to the I theta, you have changed nothing about its properties, because you always wind up multiplying a quantity by its complex conjugate. So that's something to keep in mind, that you should normalize the vector, but multiplying both the top and the bottom here by the same e to the I theta doesn't change anything. All right, but the upshot of that is we can arbitrarily, for example, choose alpha to be 1. If we don't care about normalizing the vector and we don't care about its phase, then there's no loss of generality in just choosing alpha to be 1, and I'll do it. And then later we'll come back and normalize it. So what happens if we choose alpha? Let's choose alpha to be 1, and then I'm going to call the lower entry here z. And I want to get back 1z. The question is, what does z have to be? What is the numerical value of z? All right, so let's read it off. Let's work out the equation. Let's take the top component. That's n3 times 1 plus n minus times z. n3 times 1 plus n minus times z. That has to be equal to 1. That's reading off the top component of the left-hand side and setting it equal to the top component of the right-hand side. Now, you can do the same with the bottom component. You'll get exactly the same equation for z. Okay, so I won't even bother. We obviously have enough equations here to find z. We don't need to write the second equation. Okay. So let's just solve it. We can subtract n3. We get n minus z is equal to 1 minus n3, and then divide by n minus. And we've now found an eigenvector of sigma dot n. And here it is. I'll write it out now. It's equal to 1 minus n3 over n minus. No, it's not normalized. It's not normalized. To normalize it, we have to multiply it by some number, some number. Let's just call it c. Well, let's just we have to multiply it something so that the sums of the squares add up to 1. All right. Now, what do we actually have to do to be more precise? We have to make the inner product of this vector with itself be equal to 1. Let's see what the inner product of the vector with itself is. So let's first write the row vector, the corresponding row vector, 1 minus n3. Now, shall I write n minus down here? Conjugate. And the conjugate is n plus. Okay. That's the row vector. And if I multiply this by the column vector, 1 minus n3 over n minus, then what I'll get is 1 times 1 plus 1 minus n3 squared over n plus n minus. Did I do that right? Which is what? Yeah. Let's work it out. Let's work it out. Let's multiply 1 by n plus n minus. So this becomes n plus n minus plus 1. When I square this out, I'll get 1 plus n3 squared minus twice n3. Is that right? Am I doing this right? And then we have to divide that by n plus n minus. I'm just going to take you a little ways into this calculation. Now, what is n plus n minus? That's, where did we have it? N plus n minus is 1 minus n3 squared. And so plus n3 squared, this just gives us n plus n minus is 1 minus n3 squared. The n3 squares cancel. The 1's add, and you get 2 minus twice n3 over n plus n minus. Is that right? I think that's right. Can simplify it a little bit further. Yeah, this is 1 minus n3 squared downstairs. I'm not going to do all the algebra. I'm just going to take you a little ways. Yeah, so this is, first of all, there's a 2 outside. Then there's a 1 minus n3 in the numerator. And then in the denominator, that's 1 minus n3 squared. It's 1 minus n3 squared, which is 1 minus n3 times 1 plus n3. Right. So we take 1 minus n3 times 1 plus n3. And don't worry if you're not following, because I'm going to make you do it over for homework. All right, and then we cancel out the 1 minus n3. All right, we get an answer. The answer is 2 divided by 1 plus n3. What was that? That was the inner product of the vector with itself. All right? And we didn't get 1. That's bad. That's bad. We haven't normalized the vector. What do we have to do to the vector to normalize it? We have to multiply it, not by the square root of this, but by the square root of 1 over this. We want to cancel this 2 divided by 1 plus n3. And so we have to multiply the vector, the eigenvector, by the inverse square root. So here is the normalized eigenvector. And the homework, of course, is to check this and to check that it is the normalized eigenvector over 2 times 1 minus n3 over n minus. That's the normalized eigenvector corresponding to measuring the spin along the n-axis. The same thing is true along the m-axis, except wherever you see n, you put m. Let's rewrite this. Let's actually put the square roots on the inside. Square root of 1 plus n3 over 2, and then 1 minus n3. This looks too complicated. This is more complicated than it really has to be, but 1 plus n3 square root divided by 2. That's the normalized eigenvector. Now what about the other half of the calculation? The other half of the calculation is the other vector, the eigenvector of sigma dot m. And that's easy. All we have to do is replace n by m and complex conjugate. So the appropriate row vector looks very similar. Square root of 1 plus m3, and then in the second entry, 1 minus m3. Now, instead of m minus, we'll put m plus, because it's complex conjugated, and then square root of 1 plus m3 over 2. What do we do with this mess? We take the inner product. The inner product, I'm not going to do it. I'm going to tell you what the answer is. We multiply this one by this one. Oh, there's a 2, right? 2? Nobody told me 2. We multiply this one by this one, and we add this one times this one. It looks like an unholy mess, and it is. Okay? But if you use a little bit of algebra and you just go through it, brute force, it will take you 10 minutes. If you use all the tricks, it'll take you 15 minutes. So, and you just use over and over again the fact that n plus n minus is 1 minus n3 squared. You fiddle it. I'm going to tell you what the answer is. Not for this in itself. But we have to do one more thing with this. What's the next thing we have to do with it?
Must be 0.
What's that?
It has to be 0.
Why does it have to be 0? Why? This is m, this is n. What? There's nothing orthogonal about them. If this were n, this would be a vector times its, what are you saying? If m and n were the same, the inner product would be 1. That's what we took care of to make sure of. No, they're not orthogonal. What do we want to do with them? What we want to do with it, that's, okay. Square it. Take it times its complex conjugate. It times its complex conjugate. So we take this inner product, we multiply it out. It's a big mess, but it's just a mess of n's and m's. And we take the whole thing when we get it, and we multiply it by its complex conjugate. And you sit and you calculate and you calculate and you calculate, and you can even try to throw it onto a computer and see what you get using Mathematica or something, or whatever you like, however you like to do it. But the answer is incredibly simple. I have yet to be able to find a one-line way to prove, to demonstrate the answer. I always have to do it, go through the whole thing. I'm absolutely convinced that there's a one-line argument, but I can never find it. Anyway, the answer is 1 plus n1 m1 plus n2 m2 plus n3 m3 divided by 2, or 1 plus n dot m over 2. That's the whole answer after you're finished. It has n's and m's, all of the components all over the place, and it simply boils down eventually to this expression. Now what is n dot m? Anybody know what n dot m is? It's the cosine of the angle between them. It's the cosine, let's call this theta nm, the angle between the n-axis and the m-axis. And so this is just 1 plus cosine of theta nm divided by 2. Now, first of all, one interesting thing about it is that it only depends on the angle between n and m. That means you would get the same result if you rotated the whole experiment. Okay? That's an interesting fact. And it's an important fact, of course. It's what has to do with rotational invariance of physics, that the axes didn't matter, that if you rotated the whole experiment, you would get the same answer. It's also symmetric in n and m, since it only depends on the angle between them, and the angle between them, it doesn't matter whether you write n first or m first. It's exactly the same answer if you interchange n and m. That's interesting. But let's see what it gives for various situations. First of all, supposing n and m are in the same direction. If n and m are in the same direction, then then theta is 0. All right? The angle is 0, and cosine of 0 is 1. 1 plus 1 is 2. 2 divided by 2 is 1. So the first thing it says is that if you prepare the electron pointing along the n-axis, and then you measure it along the n-axis, you will definitely find it up. You made it up, you measure it, and you find it up. That's a good thing. What about if n and m are opposite to each other? Not perpendicular, but opposite. In other words, then theta is 180 degrees. Cosine of 180 degrees is minus 1. 1 plus minus 1 is 0. Okay? That says that if you prepare the electron along the n-axis and then look and ask whether its spin is along the minus n-axis, you'll get 0 probability. In other words, if it's pointing that way, it's definitely not pointing that way. That's a good thing. What if theta is 90 degrees? And it doesn't matter. Notice, it doesn't matter. If n is fixed, m can be anywheres in space as long as its angle is fixed, so it could be on a cone. But in any case, if theta is 90 degrees, what do you get? Cosine of 90 degrees is 0, huh? Cosine of 90 degrees is 0, and so you just get 1/2, which is what we expected. But now we actually know the interpolating formula, the formula that's good for any angle. And this is the most primitive but basic quantum mechanical calculation that quantum mechanics does. So notice, I mean, think this is a remarkable achievement. We have some strange theory in where whenever we measure the spin along any given axis, it's either plus or minus and nothing in between. And yet, there's something about this system which doesn't care about the axes. You can orient the spin along any axis and measure it along any other axis. And instead of getting fractional answers, you get fractional probabilities for the result. And this is the fractional probability. Okay, are there any questions up till now? Or we could plot this function, incidentally, as a function of angle. At 180 degrees, it goes to 0. At 0 degrees, it's 1. And it looks like, whoops, no, put 180 degrees over here. It just looks like that. So we know the answer now to any question that you can meaningfully ask about a single quantum bit.
How do we know that it's the same electron?
Well, we just have one electron.
But how do we know that? We have to observe it somehow, which means to interact with it. But we cannot, because it's right in this.
Well, we build us a cavity and put some sealed walls that prevent anything from going in and going out. And we do find that that electron stays in there. We can measure the electric charge by measuring the outgoing electric flux. We find it doesn't change. So yeah, we can measure the electric charge, for example, and
We can use multiple to the experiment as well.
what's that?
It doesn't matter if you have a million electrons instead of one. The results should match for.
If we do the same thing to every one of the electrons, is that what you mean?
Yeah.
Yeah. That's right. And in practice, we can either do one of two things. You don't measure a probability. In order to measure a probability, you have to do an experiment repeatedly. Okay? You have to do the same experiment over and over again. You can do it in one of two ways. You can do this, take the same electron and continuously repeat the experiment. So you put your electron, you put your big magnetic field along the n-axis, line up that electron, and then measure it along the m-axis. Then when you're finished, you put back your big electric field along the n-axis, line it up again, and do the experiment over and over and over and over again. You can do that, or you can get yourself a whole bunch of electrons and do 1,000,000 identical experiments doing one experiment on each electron. You should get, and you do get the same answer. Okay? You do get the same answer for the probability. In the case that you have 1,000,000 electrons, the probability simply means the ratio of the number of ups or downs within the margin of error, of course. It's always margins of error.
You're saying that the 1,000,000 electrons are all covered in one experiment?
Well, you can do an experiment in which you take 1,000,000 electrons, line them all up along the n-axis. Okay? Okay, you fellows line up along the n-axis, put a big magnetic field on each one, and then measure each one's spin along the m-axis. Some will be plus, some will be minus. Okay? But the ratio of the number of pluses and minuses will measure the probability for plus and minus.
Actually, they just all have to have the same phase.
The same.
They don't have to be all lined up.
Okay, but if you really want to, yeah, right. But that's indeed so. But yes, that's true. But let's be a little bit purist about it and say we do the same repeated experiment over and over. But yes, you're right. Yeah.
If you use one electron, how many times can you repeat it and can always emit photons?
Wait, say it again.
How many photons can an electron emit?
Endless numbers. Endless numbers. It's the energy fed in by turning on the magnetic field. Okay? When you turn on that magnetic field, if the spin is in the wrong direction, you have to do a little more work to turn on the magnetic field than if it's in the right direction. And it's that energy which is effectively the photon that's emitted. So there's no limit to the number of times you can do this experiment.
Now you had defined the sigma in terms of the 3 sigma matrices.
Yes.
And one of the side effects of this was that you went from having nice, clean eigenvectors to really ugly-looking eigenvectors.
Yeah.
And
right.
Also,
ugliness is in the eye of the beholder, of course. So I mean, yeah, I mean it is. One of these days, I'm going to find a trick for this calculation so that it's not so ugly. But
the question is this a general characteristic of that type of matrix operator? And would it help if you define n as being the basis of one?
Yeah. Let me put it this way. There's another way to prove that the answer only depends on the angle between them. But that will take us into unitary matrices and things, and we'll get into that. We will get into that. And symmetries and interesting things that we haven't gotten to yet. But I could do just a simple example. I could, for example, take n to be up. Supposing I took n to be up. Let's see what we get if we take n to be up. Okay, so if n is up, m doesn't, the m eigenvector stays the same, right? M is just some arbitrary direction, right? But let's take the n eigenvector to be up. Then this is just 1, 0. Okay. Now the answer is easy. It's just this times this, plus this times this, but that's 0. All right? So the probability amplitude, the thing that you square, is just the square root of 1 plus m3 over 2. We square it, And what do we get? We get 1 plus m3 over 2. But m3 is just the cosine of the angle of m with the third axis, right? That's what m3 is. m3 is a direction cosine. In this case, the direction cosine of m. And so it actually is just cosine of that angle. So if we're willing to pick particular directions, and in particular if some of the directions are along the axis, one of the axes, then it's usually very simple.
But it's still not a unit matrix.
Which is not a unit matrix?
That, because it's...
First of all, I don't see any matrix here. This was not a matrix. This was absolute value squared. It means times its complex conjugate.
So you can set the coordinates any direction
Wait,
you want?
wait, wait. Yes.
Sigma dot m that produced those eigenvalues.
Yes. Yeah.
Yeah.
Yeah, one of the matrices was just sigma 3 by itself, which has eigenvectors 1, 0, and 0, 1. All right, so I chose this eigenvector. All right. In particular, we should check that that really is the eigenvector. Supposing n3 is plus 1. Supposing it's plus 1, okay? n3 being plus 1 just means that n is along the third axis pointing up. All right. 1 plus n3 would be 2. 2 divided by 2 is 1. So this just becomes 1. That's gone. 1 is up here, but 1 minus n3, that would be 0, right? If n3 is 1, this would be 0. So in fact, for the special case where n3, or where n is along the third axis, the eigenvector is just 1, 0. And it's the eigenvector then of just plain old sigma 3. Okay, good. So,
But you can always choose the coordinates however you want. So you can always
well, no, you're right, you're right. But there was nothing from the start that guaranteed that we were going to be able to find a find rotational invariance in the problem. So one of the things we proved by doing this calculation is that the answer is rotationally invariant. If we had independent reason to believe that the answer was rotationally invariant, then we just pick an axis.
I know I'm cheating, but all the mathematics you did was rotationally invariant. So the dot product and the eigenvector.
Well, I just picked this crazy set of 3 sigma matrices. Where did I get them from?
Yeah, that's what I mean.
Yeah,
Once you've done that,
Yeah.
you already
yeah,
agree that it's going to be.
right. But we're touching on the question of symmetries now, namely the symmetry of a system under rotation. And there's a whole subject of symmetry and quantum mechanics, which we will come to, which is which is interesting on its own. And I prefer to defer that discussion about picking axes until we have a language to speak about it in. At the moment, let's just take it as a boon, as a gift from God, that the answer came out to be only dependent on the angle between the n and m. Yeah.
So we are observing this probability.
Whoops. Ay. I'm going to get in big trouble.
So we are observing the probabilities and the gift of God that it only depends on the angle.
Yeah.
And from the physical perspective, how do we explain why is it that way?
I'll tell you, let's wait a little while. Let's wait a little while. That is the question of symmetries and how symmetries work in quantum mechanics. And it's a step that I don't want to do right now, because I do want to get to entanglement and getting entangled in... they're good questions. They're very good questions, but I would prefer just to say at this point, it's just luck. The luck of the draw. We picked the right matrices. All right. First of all, when you... leave it. Just, no. Let me just get the cookie out of the way. That's the most important thing. Yeah, another important idea that we've sort of mentioned but never really focused on is when you measure a thing, you get an answer, but then you leave the system in some new state. In other words, when you measure something, you go into the system, you interact with it, and you change its state in general. In particular, if you measure a particular quantity and you get an answer, that answer corresponds to some eigenvalue, you leave the system in an eigenvector with that eigenvalue. So if you measure the spin along the m-axis to be up, you leave the system in the state where the spin along the m-axis is up. You started with a state along the n-axis. You measured it by putting it into this large magnetic field, and you leave it in the state corresponding to the measurement that you've made. Right? So that's an important idea, that not only is it a measurement, but it's a kind of filter, which like a polarizer that polarizes photons. You measure the polarization of a photon by sending it through a polarizer, but at the same time you also leave it in the state of polarization corresponding to that polarizer. Same idea here, that the electron is left in an eigenstate of whatever it is you measured, corresponding to the value that you measured. Okay. Let's see. Oh, there's another interesting theorem. No, let's, yeah. Can you do a single measurement or simultaneously two measurements that measured both sigma 1 and sigma 2 simultaneously? Can you do a measurement which measures both of them and doesn't screw up somehow? And the answer is no. And the answer is very simple. The reason is very simple. The eigenvectors, if you measure sigma 1 and you get an answer, and you measure sigma 2 and you get an answer, remember, the rule is that you leave the system in an eigenstate corresponding to that measurement. Okay? Okay. You've got your A.
Just carry on.
All right. Now the problem is there are no eigenvectors in common between sigma n and sigma m. They have different eigenvectors. They are not in common. Therefore, you cannot measure them both simultaneously because you cannot leave them in a state which is both an eigenvector of sigma dot n and sigma dot m. There just are no eigenvectors which they share. Right? So no, it is not possible to measure them. But an interesting question is, what is the condition, the mathematical condition, that you can measure two quantities simultaneously? And the answer is that they had better have all the same eigenvectors, that the eigenvectors of one of them had better be exactly the same as the eigenvectors of the other one. Because if you measure them and you get an answer, then the answer has to be an eigenvalue. And the eigenvalues correspond to distinct eigenvectors. And the only way that you can ever measure two quantities simultaneously and be sure that you'll get answers is if they share all the same eigenvectors. What was that? If two matrices share all the same eigenvectors, they have a property. The property is they commute. Okay? Now, this is again something I do want to get to where I'm going tonight, but let me write that as a theorem on the blackboard.
You can attempt a measurement, but
What's that?
you can measure and get the right answer, or they don't disturb one another. You can do the measurement, but you may
Well, how would you measure sigma x and sigma y simultaneously?
you can do the physical experiment.
How? Remember, you measure sigma x by putting it into a large magnetic field along the x-axis. You measure sigma y by putting it into a large magnetic field along the y-axis. Well, you can put it into a magnetic field which is both along the x-axis and the y-axis, but then you'll be measuring, you'll be measuring not sigma x or sigma y, but sigma along a 45-degree angle. You'll be measuring something different. So the answer is you'll never think of a way of even measuring it, but that's good because the mathematics says you shouldn't be able to. All right, the condition, if I have two matrices, that they have all common eigenvectors, I'm going to write the condition and either look up the proof of it, prove it yourself. It really is a one-liner. This really is a one, well, maybe 2 lines at most. But if 2 matrices, A and B, have all the same eigenvectors, let's call them alpha sub I. These are the various eigenvectors. No, that's not what I want to write. Lambda I. This is the ith eigenvector. Wow. Alpha I. Yeah. And another matrix has exactly the same eigenvectors, but perhaps different eigenvalues. Let's call them mu. Mu I times alpha I. In other words, the same set of alphas are the eigenvectors of both matrices. Then you can measure them simultaneously, the 2 quantities, if they have the same eigenvectors. And under those circumstances, there's a theorem that's a one-liner, as I said. It says that A times B is equal to B times A. Or in mathematical terminology, well, or A minus B, AB minus BA is equal to 0. Remember, the order that you multiply matrices is important. When you multiply matrices, it's important. If the matrices commute, that means it doesn't matter which order you write them in, then all of the eigenvectors are simultaneous eigenvectors of the 2 operators. That's a theorem. Necessary and sufficient condition for all of the eigenvectors to be the same are that the matrices commute. Commute means you can interchange the order. Another way of writing the same thing, the mathematical notation for AB minus BA is to just write them in a bracket. Not a bracket, a commutator. This is called a commutator, and it means AB minus BA. If 2 operators commute, you can measure them simultaneously because they have exactly the same eigenvectors. That's a theorem, and as I said, it really is a 1 or 2 line theorem. You know how A acts on, just multiplies by a number, and then you know how B acts, it also multiplies by a number, and so you can easily figure out what the product of A and B is on any vector, on any eigenvector, and from that you can conclude, you can make your conclusion. So I don't want to go through the proof of that because it take us astray, but I do want to get to, okay. There is one more theorem about the simple spin, and it's a very interesting theorem and an important theorem. This one is really quite important. It's a theorem about the single spin. What it says is that no matter what state you write down, what vector, in other words, any vector you write down, alpha, beta, with presumably alpha star alpha plus beta star beta equals 1, assume that. So that's normalized. No matter what state you write down, there is always some direction of space such that if the electron is in this space, if the electron is in this state, then the spin along that direction is definitely plus. In other words, any vector that you write down is an eigenvector of some sigma dot n. Given an alpha and beta, you can find a direction in space such that this is an eigenvector. Let's write it alpha beta equals alpha beta with any alpha or beta. In this case, the problem is not finding the eigenvector. Given an n, you can look for an eigenvector. This is the reverse problem. Given the state of an electron, can you find the direction along which that electron is definitely up? And the answer is yes. And the simplest way to prove it is to count think of this as equations. Alpha and beta are fixed numbers, okay, fixed complex numbers. This is an equation for the components n1, n2, and n3. Okay. The simplest way to prove it is simply to count the number of equations and the number of variables that you have. The number of equations is the same as the number of variables. Basically, there are two equations, one for the top component and one for the bottom component. How many components of n are there? Yes?
I think sigma dot n is up there on the board, and it's
Yeah.
got n3 and n plus. So there are two variables.
Yeah, no, there's only two variables. There's two variables, two real variables, because nx squared plus ny squared plus nz squared is equal to 1. In other words, n is a unit vector, and so the number of variables that it takes to describe it are two angles, longitude and latitude, okay, on a sphere. So there are two variables, there are two equations, two unknowns, and the number of unknowns and the number of equations is the same. You can check that. And so there's always an n. There is always an n, given any vector. So what that says is that if you take here's the way you might do the experiment. You've made an electron in some definite state, okay? But you're not sure what direction it corresponds to, right? You're not sure. You did something with the electron, and you weren't clear. All you know is somebody put a magnetic field on it and lined it up along some direction. Or I don't even know what they did. Whatever they did something, and they left the electron in some state, and we would like to find out if there is a definite direction along which the spin is up. So here's what we do. We, first of all, make a whole bunch of replicas of the same experiment. So we have a whole bunch of electrons, all identically prepared. All identically prepared. Now we measure, now we use and how many of them? 100 zillion of them. We're going to use the first 100 million to find out which direction the spin is pointing. And then we'll check all the rest of them and check and make sure that they really are all pointing in the same direction. So what you can do is you can measure the spin of the first one along some arbitrary axis. You can measure the first 100 of them along that axis. If they all point up along that axis, it sounds like there's a good bet that they're up along that axis. And then you measure all the rest of them, and you find them all up. But you might find that if you measure along the z-axis, you'll find some up and some down. Okay? If you measure the first 100 of them and you find some up and some down, change direction a little bit. Change the direction of your magnet a little bit, and check another 100 of them. If you still find there are some up and some down, change the direction of the magnet again. Keep changing the direction of the magnet until you find the direction where all 100 or all 1,000 test electrons are definitely up. Then, when you found that, you will find that all the rest of them are up. Okay. 1,000 may not be a big enough number. You may have to use 10,000, but that's the idea. There is, for any state of an electron, no matter how you prepare it, if you prepare it carefully, there will be a direction along which it is definitely pointing in that direction. Yeah?
Well, the n has 2 degrees of freedom, right?
The n has 2 degrees of freedom.
No, but alpha and beta are very complex.
Right. Good. Very good. So it sounds like there are 4. It sounds like there are 4.
But you have that,
Right.
the normal.
Right. We have the normalization, but we also have the freedom to change the phase. We also have the freedom to change the phase. So there's no, the phase drops out of the equation also.
And don't you need an eigenvalue?
1. Well, we're looking for a direction such that the eigenvalue is 1. We're searching for some direction that the eigenvalue is 1, and this gentleman over here asked exactly the right question. He started counting variables. How many equations are there? Well, there's as many equations as there are components of alpha and beta. Okay? There are 4 complex components. This equation reduces it down to 3, But then the fact that that the overall phase of the wave function that you can doesn't matter in this equation either. In other words, multiplying it by both sides by e to the I theta doesn't matter. And so really there are only 2 degrees of freedom in writing down a complex vector for an electron. 2 degrees of freedom, 2 variables here, 2 independent interesting variables here, 2 of them here. And so the number of equations is the same as the number of unknowns.
Does the phase have any physical meaning then?
The overall phase of the wave function does not have, or this is called a wave function, the overall phase of the state vector does not have a physical significance. Why not? Because whenever you calculate any physical probability, you always wind up multiplying it by its complex conjugate. When you multiply by a complex conjugate, the phase goes away. Okay? So the answer is there are 2 variables, 2 physically interesting variables that go into defining the state of an electron. And they're in one-to-one correspondence with the 2 physical variables that define a directionality in space. So you can make a correspondence between the components here and directions of space. All right. That's true of single electrons, everything I said. Now, I am going to continue because, well, let's see. No, we can take a 5-minute break. Let's try to get to entanglement today. To get to entanglement, we have to think about. I'll tell you something. I went to a middle school, and I taught a bunch of 10-year-olds about string theory and extra dimensions and all that stuff. It was kind of interesting. Teaching them was very much like teaching you guys. No. It was. They're unafraid to ask questions. They're boisterous. They're fun to teach. It's the people in the middle, the undergraduates, who are just terrified of asking a question, just no fun to teach. One kid asked me a brilliant question. He said, the neutrinos, there's all these neutrinos around. Are those the things that give me headaches? But, you know, it really has the same feel. We're going to begin now studying pairs of electrons. To get to the basic idea of entanglement, all we need is 2 electrons. But just before we do that, I want to make a table of the action of the sigma matrices. I just want to write sigma 1 on up. What does sigma 1 on up give? Sigma 1 is the matrix which interchanges up and down. It's off diagonal, and it means that it interchanges. It takes up to down. Sigma 1 on down equals up. Sigma 2, what does sigma 2 do on up? Well, sigma 2 and sigma 1 are very similar, except there's an I in there and a minus sign. So actually what sigma 2 on up does, anybody know? Well, it gives you down again, but it gives you down with an I in front of it. And sigma 2 on down gives you minus I times up. You can check that just from the matrices. And finally, sigma 3. What does sigma 3 do when it hits up? Just goes up. Up is an eigenvector of sigma 3 with eigenvalue +1. So it just gives up. And sigma 3 on down gives minus down because it's an eigenvector with minus sign. This is an abstract representation of the sigma matrices. Well, it's not abstract; it's concrete, but it has the same content that the matrix structure has. Now let's come to pair of electrons. And when I speak about a pair of electrons, once again, I'm not concerned with their position. I imagine that they're nailed down, they've been nailed to the wall, and the only thing that's free to vary is the spin of the electron, the little magnetic moment that it carries. And now we have two of them. We have two of them, and we're interested in the space of states, the possible configurations of two spins. Now again, I can measure the spins, for example, along the third axis, and use the measurements along the third axis of the two spins. And I could choose the same axis. Just for simplicity, I will choose to measure them along the same axis and label them very similar to the way I label the single electron. But now we need two labels. So for example, here's, in fact, we can write down all of the states. Let me write down all the possibilities. We have, in the first entry here, will correspond to the first electron, and the second entry will correspond to the second electron. So this means electron number 1 is up, and electron number 2 is up. We'll never get confused about which electron is which. One of the electrons is nailed to the blackboard over here, the other one is nailed over here, and we call this 1 and we call this 2. So there'll be no confusion about which electron is which. This is electron 1 up, electron 2 up. And then there's a state in which electron 1 is down and electron 2 is up. And then there's another one in which electron 1 is up, but electron 2 is down. And then the last one, down, down. That's all there is. Those are all the possibilities that we can get. 4 possibilities, 2 times 2. These are the 4 possible states of two spins. And so we're evidently dealing, obviously, with a 4-dimensional vector space now, with 4 basis vectors and 2 sets of quantities, 2 sets of observables. Now, the 2 sets of observables are, of course, the spins of the 2 electrons. How am I going to label the 2 spins of the electrons? I can't call them sigma 1 and sigma 2 because I've already used sigma 1 and sigma 2 for something else, for the 2 components of the spin of 1 electron. So I need another name. The first one I will continue to call sigma. The second one I'm simply going to give another name. Tau follows sigma in some alphabet or other. So we're going to label the first electron spin and just call it sigma. It has 3 components, same as it had before, sigma 1, sigma 2, and sigma 3. And the other one I'm just going to label tau, and it also has 3 components, tau 1, tau 2, and tau 3. How do the spin operators for the 2 electrons, how do they operate, and what do they do to these vectors? Let me teach you now how you think about. First, let's take the first electron. What does the spin operator, sigma 1, and sigma 2, and sigma 3, do to these 4 state vectors? How does it act on these 4 state vectors? And here's the answer. If you're interested in the first spin, the one on the left here, you simply turn a blind eye to the second one. You don't look at it. It's passive. The operator sigma, which refers to the first spin, has no action on the second electron. It does nothing to it. So when sigma acts, it may or may not flip the spin of the first electron, but it leaves the second one completely unchanged. All right, that's the rule. Now, this rule, of course, is an empirical rule, but it sounds reasonable that the spin of the first electron should only act on the first electron, on the coordinate of the first electron. So, for example, let's do 1 or 2 examples. What does sigma 1 do when it acts on the state up-down, just as an arbitrary example? Well, you just turn a blind eye to down. And in fact, when I say you turn a blind eye, I mean we will not change the down for the second electron. But we'll do to the first electron exactly the same thing that sigma 1 did on the first electron. What did it do? It flipped it down. So, turning a blind eye to the second electron, sigma 1 makes down, makes the first electron down. has done nothing. The second electron is completely passive. Sigma 1 does that. Okay. Let's do another example. Let's do sigma 1 on down, down. Well, again, it does nothing to the second electron, and it flips the first electron up. Up, down. Okay, so you see what I mean by saying the second electron is passive. Now let's ask about what tau does. Tau are the operators associated with the second electron. They also do something to the state vectors. This time, you turn a blind eye to the first electron and allow the operator to act exactly the same way, except substitute sigma for tau, exactly the same way, but as it applies on the... before I do that, let me do one more case of sigma. What about sigma 3 on, let's take an arbitrary case, up, up, down? What does this give? Well, sigma 3 on up leaves up with a +1. So it does nothing. Up, and the second one is passive, which just stays the way it is. What about sigma 3 on down, down? Well, you look over here on this chart. Sigma 3 takes down to down, but with a minus sign. So it gives you minus down, down. In other words, the second electron just goes along for the ride. What about the taus? The taus act on the second electron, and the first electron goes along for the ride. So let's do one or two cases. Let's take tau 2 and act on up, down. All right, so to see what it does, we go over to the chart. We're acting on the second electron being down. So we go over to sigma 2 on down, and it gives us minus I times up. So this just gives us minus I times up, up. The first electron has been passive. Nothing has happened to it. The second electron has responded exactly the same way to tau 2 as dictated by this chart here. That's a set of definitions. That's a set of definitions of what sigma and tau do. If you know what sigma and tau do to all of the various vectors, to all the independent vectors, then you also know what they do to any linear combination of them. So this is a complete specification of how sigma and tau, all components of them, act on any vector. Yeah.
Why is the minus I outside of the cat? I mean, you did that on the left, in your table on the left, and it sort of slipped by, but now it's got significant implications because the minus I is affecting both the electrons. Why not put the minus on the inside?
Well, multiplying a vector by an I, it doesn't matter where you put. It doesn't make. There's no meaning to putting it inside the vector. You can multiply a vector by a constant, but the constant, it's a notational notation, standard notation, to leave the constant on the outside of the vector.
To put it another way, the inside of the cat is just a label.
Yeah, it's a label, right. Right, that's right. It's a label. It's just a labeling configuration. It's not. It doesn't make any sense to multiply the label by a number. So it goes on the outside. But yeah, but you are. Yeah, I mean, you wouldn't be able to tell from this equation alone, whether this I was because of this up or that up. But if you look at all the various possibilities, you know, here's this tau 2. Let's write all the various things that tau 2 can do. Let's first do up, up. So tau 2, let's see, we have to see tau 2 on up gives I times down. So that's I times down plus I times down, and so forth. We can go through the list of them. The point is we know what sigma and tau do to every one of the vectors. And so we know completely what the nature of these operators are. We don't have to bother writing down matrices. We know what they do. That's enough for us for now. We could invent matrices describing them, but it's unnecessary for the moment. Maybe later we'll do it. No, it's just, well, it's just multiplication by I. It's not physically, it's just multiplication of the vector by the number I. It doesn't represent any rotation in real space, if that's what you're asking. It does not represent the rotation in real space. It's just the action of these matrices. That's all. That's what the matrices do. And they just do the same as they would have done had the other label not been there. That's Now, how many, over here, this gentleman over here remarked before about the number of variables that it takes to specify the state of an electron. And the answer was 2. The answer was 2 independent real variables that are important in specifying the state of an electron. Okay? How many do you think it takes to specify 2 electrons? That's what you'd think, wouldn't you? Okay, but let's go through the counting. There's a 4-dimensional vector space. You can, where are they all? Up, up, down, 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 down. What states can you build? You can multiply each one of these by a complex number and add them all together. That's the most general state of 2 electrons that you can write down. The linear combination of arbitrary coefficients, subject to the constraint that the sums of the squares are equal to 1, and that the phase doesn't matter. Now how many are there? What's the counting now? 6. 8. 4 complex numbers. Yeah, we have to remove 2, right. Right. 4 complex numbers, that's 8 variables, 8 real variables. Remove 2, that gives you 6. Right. Something's going on here. There seem to be more possibilities than you might have guessed had you said each electron itself can be in some state. If each electron was in some state, each electron requires 2 variables to define its physical state, you might have guessed the answer was 4. Okay? It seems that the space of states must somehow be richer. It must contain things which cannot be described simply as each electron having its own state, because there are just too many variables, just too many possibilities. Instead of 4, there are 6, so 6 variables, 6 independent real numbers characterizing the state of a 2-electron system. All right. This is entanglement. But first let me tell you what corresponds to a pair of electrons, each with its own state. Each with its own state that you would recognize as supposing the state of the electron number 1, or supposing we put the electron number 1 in the state alpha up plus beta down. And let me put a 1 here to indicate that this is electron 1. That's electron 1. That's the state of electron 1. And now what about electron 2? Electron 2, I'm going to write alpha 2 times up plus beta 2 times down. I'm not going to write it. It's state of 2, state of 2. Now, neither of these are really 2-electron states. 2-electron states have to have 2 indices. What if electron 1 is in this state and electron 2 is in this state? Then the 2-electron state you write down the following way. You write it as a product. Alpha 1 up, and then I'll tell you what to do with it. Alpha 1 up plus beta 1 down times, let's put a bracket, alpha 2 up plus beta 2 down. And then read off from this the following object. Alpha 1, alpha 2 times both electrons up, up, plus alpha 1, beta 2 times the first electron up, the second electron down. Then beta 1 alpha 2, beta 1 times alpha 2 times down up. And then finally, plus beta 1, beta 2, down, down. This 2-electron state, which was obtained by combining two 1-electron states, corresponds to a state in which each electron has comfortably been placed in its own state, sort of independently. That's what this is. If you were, for example, to take such a state, you would find that there is some direction in which sigma 1 is definitely up. Remember, for any electron state that you can make with an alpha and a beta, there is always some direction in which sigma dot n is up. This state has that property. With the same, just using alpha 1 and beta 1 in the same way, you'll find a direction in space such that sigma 1 is definitely positive. It'll be the same direction as you would have gotten by just looking at the 1-electron system by itself. Same thing for the 2-electron, for the second electron. There exists some direction, a different direction in general, a different direction in which the second electron is also pointing along the positive axis. You can check that if these two states have the property that this one is definitely along the n-axis and this one is definitely along the m-axis, then you can check that the thing that you've composed in this way has the same property with respect to the more complicated 2-electron system. Remember, sigma 1 only acts on the ups, on the first electron, sigma acts on the first electron, tau acts on the second electron, and you can check that, that this 2-electron state has all the properties you would expect if you simply had two distinct electrons that had been prepared completely separately, never talking to each other, independently. Not necessarily in the same state, two different states. For example, if you just put electron 1 in magnetic field pointing this way and electron 2 in magnetic field pointing this way, and let them come to rest and let them give off their photon or not give off their photon, then that's what this kind of state would be. It's called a product state. It's a simple product state, and it always has a pair of directions along which each electron is polarized. That's the word. To say that the electron is definitely up along some axis is to say it's polarized along that axis. Now I'm going to construct for you a state which obviously doesn't have that property, which does not have the property that there's some direction along which the spin is up. Okay? And it is an entangled state. It's one that does not have the property that you can think of it as two separate electrons which have been prepared independently, each one with its own state. Somehow the electrons are more intricately entangled. The state of the electrons are more interestingly entangled. Here's a state. It's very simple. One electron is up. One electron is up, the other electron is down. And you add to that the first electron down and the second electron up. Of course, you'll have to put a 1 over square root of 2 to normalize it. But the 1 over square root of 2 is not going to play any role in what I say. Here's a state, and this state has the property. If you think about what the state means, it has the following property. That if you measure electron number 2 and find it's down, then electron number 1 must be up. And if you find electron number 2 up, then electron number 1 is down. This state has a funny property that if you know that it's in this state, if you happen to know that it's in this state, the combined system, then you would learn something about the second electron by measuring the first electron. Okay? All right. This state has the property that if you measure the second electron to be down, then the first electron is up. And if you measure the first electron, second electron to be up, the second one is down. Nah, the first one is down. You know what I mean. I'm getting tongue-tied. It's getting too late. Let me prove something to you. Let me prove that every one of the sigma matrices, as well as the tau matrices, has average value 0 in this state. Right? Remember how to calculate the average value? You sandwich the operator that you're interested between the state and its the same state on one side and the other. Okay. Supposing it were true, supposing the expectation value of all three of the sigmas was 0, then it will also be true that the expectation value of any sigma dot n will be 0. If the expectation value of sigma n dot n is 0, that means that there's a half a probability for it to be up along that direction and a half a probability for it to be down. So if all of the expectation values of all three sigmas are equal to 0, then there can be no direction along which sigma is definitely up, because along any direction the probabilities are a half. So let's see if we can prove that. Let's take the three sigmas and check. First of all, we have to make a bra vector out of this. All of the coefficients are real, so there's no complex conjugation. If the 1 over square root of 2 is not going to play any interesting role here. It doesn't do anything. Let's make the corresponding bra vector. The corresponding bra vector also is the sum of two terms. And it's up, down, plus down, up. And now let's, I don't know, pick a sigma. Let's start with sigma 1. Sigma 1, and then same state, except the ket version of it, up, down, plus down, up. Okay, now we know how sigma 1 acts. What does sigma 1 do? It acts on the first entry here, and it changes, it intertwines up and down. That's all it does. It changes up to down in the first entry and down to up. So sigma 1 on this state here gives us up goes to down, 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 and takes this down and makes it up. The other side here, I've done nothing. Up, down, plus down, up. What's the inner product of up, down with down, down? Well, I didn't tell you. But the answer is 0. They correspond to physically different situations where one electron, which was up over here, is down over here. That always means they're orthogonal. That always means they're orthogonal. Different labels always correspond to orthogonality. Up, down, 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 and down, up are all mutually orthogonal to each other. That's an assumption, but it goes together with the idea that these are measurable, distinctly different configurations. So we have an up, down, and a down, up over here, but no up, down, and no down, up over here. So these must be orthogonal. Everything here is orthogonal to everything here, and the inner product is just plain 0. You'll only get something if there's something common between the bra vector and the ket vector. That's the only way you can get something non-zero. That's the expectation value of sigma 1. What about the expectation value of sigma 2? Well, sigma 2 does about the same thing that sigma 1 does, except it throws in some i's and some minus signs. But still, there's up, down here and down, up. Over here, there's only down, down, and up, up. So it's still orthogonal. This is still orthogonal to this. And the expectation value of sigma 2 is 0. we found the expectation value of sigma 1 is equal to 0. The expectation value of sigma 2 is equal to 0. The only one left is sigma 3. Okay, so let's check sigma 3. What does sigma 3 do on this? Well, keeps it up, does nothing. What does it do to this one? Minus sign. So sigma 3 just multiplies this one by minus. Now let's look at the inner product. What's the inner product of up, down with up, down? 1. What's the inner product of up, down with down, up? They're different situations. 0. Down, up with up, down? 0. And up, down, sorry, down, up with down, down, up with down, up is 1, but there's a minus sign. So we found all 3 expectation values are equal to 0. We've encountered a situation which is impossible if every electron had its own state in the same sense that it would have a state as if there was just a one-electron system. For any one-electron system, there is always some axis such that sigma dot n is equal to 1, that the expectation value of sigma dot n is equal to 1. And incidentally, in any eigenvector of a quantity, the expectation value is just that eigenvalue. So there's always some direction that sigma n is equal to 1. But if all 3 components of sigma have 0 expectation value, then every sigma dot n expectation value is equal to 0. So in every single direction in space, the probability is a half to find the electron up or down. This is something new. When we concentrated on single electrons and prepared them in magnetic fields, no matter how we prepared it with a magnetic field, we found directions where the electron spin was pointing in that direction. Now when we have 2 electrons, in this interesting state where measuring one tells you something about the other, we find something new. We find that there is no direction, or in every direction, the expectation value of sigma is equal to 0. Equivalently, any direction that you measure the spin along, you'll find 50-50 probability that it's either up or down. There'll be no bias toward upness or downness along any axis whatever, which is quite different than you might have expected if you just had independent electrons, prepare them with magnetic fields. This is something new, something that cannot be if the only possible states were the ones that were like just having 2 independent electrons prepared. It's called an entangled state. And as I said, the one way you can read off that it's entangled is from the fact that if you measure one, you learn something about the other. Okay. Now, how odd a phenomenon is this? We're going to dwell on this at length, but this is our first experience seeing quantum entanglement.
I'm a little confused, though. You're trying to make, I guess, what I'd call a direct measurement of the first one gives nonsense, which is a contradictory thing. But you started off by saying, well, another way to do this is to measure the spin of the second one. And then you could say something about the spin of the first one.
Yeah. Two separate things.
Trying to measure the spin of the second one, it's
let's for a minute forget the statement about measuring one and learning something about that. Let's forget that for a minute. All right. So we found a system that no matter what direction you put the magnetic field on electron 1, forget electron 2, no matter what direction you impose the magnetic field, you'll always find 50-50 probability. This is something that would not have happened had you created the electrons independently by their own magnetic field. It's another question, how do you create electrons in this state over here? And we'll come to that. But for the moment, apparently in the mathematics, there are a collection of state vectors, or a collection of quantum states, which have properties that that are odd. Now, they do have the property. We're going to come to this in a moment. We'll come back to it. Supposing you measure electron 1 and find it in some state, do you learn anything about electron 2? The answer will be yes. And it will be just as you might expect. As I said, if you measure electron 2 up, you will find electron 1 down. How odd is this from a simple probability point of view? Well, in some sense, it's not that odd, in some sense. Supposing I have, a penny and a dime, okay? And I take the penny and a dime. Well, let's suppose for the moment that, that the penny and the dime are exactly the same size, so I can't tell the difference with my hand. And I take them and I shake them up, and without looking, I grab one and I grab the other and I take them far apart. Guess what? If I look at this one and I find it's a dime, I instantly know this one is a penny. Likewise, if I look at this one and I find it's a penny, I instantly know this one's a dime, right? Without any lag, without any time lag. So that's a classical version of entangled probabilities. It's not all that odd. Question? Or at least at first sight, it doesn't seem terribly odd. The difference, well, I think we'll come to it next time, what the difference is. There is a difference, and we'll come to it. But just from a simple probabilistic point of view, let's say just measuring the upness and downness of electrons, at first sight, it seems no odder than the situation where I have a penny and a dime. I shake them up and I don't look, and I ask about the probabilities when I take them apart. You know what? First of all, there'll be 50-50 probability that it's up or down, either one of them, no matter which one I look at, if I only look at one of them. But if I look at one, then I instantly know what the other one does.
Only if you're sure that you have a penny and a dime.
Only if I'm sure that I had a penny and a dime. Exactly. And the corresponding thing is true here. Only if I'm sure that I've prepared the two-electron system in this state. Only if I'm sure that I've prepared the two-electron system in this state.
Question, when you make the sigma 3 measurement, you're measuring for both of them being up. Is that what you're doing?
Again?
When you make when you make a sigma measurement on both of them.
No, it's just a measurement. When you make a sigma measurement of both of them. Yeah.
Of this pair.
Well, yes, you might. Yeah.
And the probability that they both will be up is 0. Is that?
That is true. The probability that both.
Is that what you mean?
It is true that the probability of both of them is up to 0.
Right, because essentially they're pointing. Yeah. Classically, you would say they're.
Yeah, I can tell you something else. You can define a new observable quantity. The product of the two sigmas. Well, that's not a good example. This is not the right state. Okay, well, yes, but what you no, what I'm going to say is wrong. What is it that you said? You said that the that.
You're not just measuring one of them and finding the other one is in the opposite direction. You're measuring both in one measurement and finding that
if you
they're both
right,
up. Both
right. If you measure both in one measurement, you will find they're opposite. But you could say you don't have to measure them both simultaneously. You could measure one of them over here, and then your friend down there, it doesn't even have to be you, your friend down there can measure the other one. And then you can communicate, and then you can come together and talk about what you discovered and so forth. You can be sure that if you discovered a penny, you can be sure that when your friend comes over and tells you what she discovered, that it will be a dime, unless something intervened.
It seems to me it's like you had the penny and the dime mounted on a rod so that when one of them was heads up, the other was heads down, and you didn't see this rod, but no matter how you shook it, you would never get two heads or two tails because they're connected.
Well, there are ways you could shake it that you might disturb it,
but I mean, one of them would be up. I mean, because they're welded together.
Well, no, in the classical case, you just started with a penny and a dime, so you just know that there's always a penny and a dime.
Well,
unless of course some alchemist takes the penny and turns it into a dime. So I mean, there's an assumption going on here that nobody disturbed. Yeah, exactly. Right.
I was taught the law of large numbers to find probabilities and statistical analysis.
Yes.
And I was wondering,
what there is about this that the law of large numbers is not used for?
No, we're using the laws of large numbers in many cases. We're using the laws of large numbers, but at the moment I'm not. But in many cases, when I say the expectation value of something, the expectation value is something that you only measure by doing many, many repeated experiments and gathering data. But in this very simple case of the penny and the dime, I need only do one experiment. If I do one experiment and I find that penny, I know that the other person will find a dime. Now, you may want to do this over and over again. You may want to collect data. So you may want to do the same experiment over and over and check that it really works. That every time I find a penny, she finds a dime. Every time I find a dime, she finds a penny. So we would perhaps like to do this experiment over and over and over again and check that statistically this correlation, it's called a correlation, that this correlation exists between what she measures and what I measure. It would be necessary to do it over and over again and collect statistics about it. But what we should find is that every single time we do it, there will be, we could call it an anti-correlation between what one person sees and what the other person sees. Okay? So entanglement of probabilities is not that odd a thing. It just means you know something about the combined system and that something doesn't get disturbed perhaps as you separate the things. The odd thing is you could separate the two people, one with a penny and one with a dime, take her off to Alpha Centauri, where it takes 4 years to get information from one to the other. Nevertheless, the instant I look at my penny, I know what my friend out there will find. She doesn't, but I do.
You're not saying that setup is what we should be thinking about.
At a classical level, that's what you should be thinking about. But we're going to find that's what Bell's theorem is about. Bell's theorem is about the difference between the situation that I just described and the corresponding quantum system.
If you look at this calculation, it seems to be evidence that this thing can't even exist, right? I mean, that's what it looks like.
Yeah, but we know how to make it. This. Yeah. Let me put a minus sign in here. It won't change anything. Nothing will change. We'll put minus signs here, but then it'll have exactly the same effect. Okay, it's a better state. Okay, here's how you make it. Remember that each electron is itself a magnet. I'll first of all tell you what this state corresponds to. It corresponds to the magnets being oppositely oriented, but without any preference for which direction. All right. So whichever way one magnet is pointing, the other one is pointing in the opposite direction. And that naturally happens if you bring two electrons. Together, because bringing one electron into the field of the other electron, one electron wants to respond to the other electron and make its magnetic moment in the opposite direction. So if you brought the electrons together in some wrong configuration, they would emit a photon and jump to an opposite configuration. So all you have to do is bring the two electrons together, leave them for a while. A photon either will or won't be emitted, and after a while they will be in this state. They'll be in this state because the two magnets will try to anti-align each other, but there's no particular preference for them to anti-align this way, this way, this way, and so you'll have something which is the same in every direction, but no matter what direction you measure the spin, you'll find that the other one is in the opposite direction.
So the preparation here is just to have two electrons.
Is what?
Just to have two electrons in proximity.
Yeah, really, that's right. And just bring them together and leave them for a while. And they'll go into this so-called singlet state. This is the singlet state of two electrons, yeah.
This is the same as the Pauli's exclusion principle.
No. At the moment, there's no exclusion principle. We don't have to think about the exclusion principle for the reason that we've definitely put the electrons at different places in space. All right? If they're in different places in space, then there's no issue about the Pauli exclusion principle. Yeah, if you bring them so that they're wave function, yeah. But as long as they're nailed down and we know where they are, you don't have to bring them on top of each other. You just have to bring them close enough that their magnetic fields interact, can feel each other. And then if the electrons are parallel, that's like having two magnets which are parallel. The north poles repel each other, and it has more energy than if they're anti-parallel. And so what will happen is it'll emit a photon and somehow come out with opposite polarization. And this is what will happen to those two electrons. So it's really just using one electron as the magnet which polarizes the other electron. Yeah.
So in an electron beam, you have a pair of electrons?
Yeah, pair of electrons.
So basically pair of electrons that moves.
Say it again?
In one electron beam. You have an electron beam.
Electron beam, oh. Well, if you have an electron...
Do I have a pair of electrons that move?
You have to... All right, if the electrons are far apart from each other, and in an electron beam, the electrons are very far... No, they're very far apart. Oh yes, an electron beam is a very, very dilute thing. Okay, believe me, electrons are very, very far apart by comparison with the length scales inside an electron.
Well, imagine they cross over on an electron beam.
They cross over. You mean they hit each other? No. Right. If you have two beams of electrons, then something. They still don't get all that close to each other. They still, an electron and a single beam, to a good approximation, they don't interact with each other very much. There is some Coulomb repulsion between them, but there's very little spin-spin interaction between them. They're too far apart. It's too dilute.
What's the distance to the interaction?
What's that?
What should be the distance to the interaction?
Okay. The magnetic moment has units of length. The magnetic moment is the magnetic charge times the distance between them. Okay? So the magnetic moment has units of length, and that's the length which sets the scale about how close the electrons should be. So in other words, they should be within that, roughly within that distance, and then in a fairly rapid time. Look, it's a question of time scales. No matter how far apart the electrons are, they will eventually settle down to their ground state, which was the opposite. Eventually they will. It's a question of how long you're willing to wait for the photon to get emitted. So if the electrons are far apart, then the difference between the energy of two parallel ones and two anti-parallel ones is so tiny that the photon that's emitted is such a long wavelength photon, it just takes a very, very, very long time for that process to happen. So in a typical electron beam, there just isn't enough time for the electron magnetic moments to feel each other very much. Now, of course, if the electrons collide, then in fact, you do make states like this typically. So that does happen. But,
so what should be the distance between two electrons in such a way that they interact?
10 to the minus 11 centimeters or something like that. Yeah.
Why does that state have a minus sign in it instead of the plus sign?
Oh, we'll have to do that. We'll have to. Yeah. No, that's by no means obvious. That's far from obvious. Right. Right. That's far from obvious. I will tell you, but I'll tell you the answer anyway. I'll tell you the answer anyway. No, I won't. I'll tell you the answer next time. Time to go. Time to go.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.